You want to move a 500 Newton microwave across a level floor, and to start the microwave moving, you have to pull it with a 230 Newton horizontal force. Once the microwave starts to move, you can keep it moving at constant velocity with only 200 newtons. What are the coefficients of static and kinetic friction, which quantifies the stickiness between the microwave and the floor? So first of all, let's acknowledge this may not be the best way to move a microwave. You should probably pick it up. But let's begin with drawing a simplified picture of what's going on. The microwave, which I'll draw as a box, and the floor. And let's assume that this is the x direction. The forces I'll just go ahead and draw in red. We know that there's a force of gravity pulling down, so I'll write that here, force of gravity, which obeys a simple formula, mg. There's a normal force provided by the floor pressing upward. There's an applied force from the pulling, F applied, which is equal to, well, it depends on which part of the problem we're talking about. So let's just leave it there. And there will be some frictional force acting between the microwave and the floor, and I'll call that FF. And it could be kinetic or it could be static friction, depending on where we are. So we have a picture. Let's clean this up even more and draw a free body diagram so that we can make it as simple as possible. Here's the microwave. We've got the force of gravity, mg, a normal force pointing up, the applied force like this, and a frictional force like that. The kinds of concepts that we might need. Well, there are things moving, but we're not told anything about position or time, so I don't think we need kinematics. But we definitely need to know something about forces. We need to know something about Newton's laws. And since we're dealing with friction, we need to know something about the models of friction that we use. So I'll write friction models, and by that I mean kinetic friction and static friction. So, what are the relevant equations that we might need if those are the concepts that might be relevant? Newton's laws, Newton's second law in particular, the net force on an object is equal to the mass times the acceleration. And every time we do that, it's the net force on that object, the mass of that object, and the acceleration of that object. It's a vector equation, which means that each of the components of that vector equation work, so in the x direction and in the y direction separately. We also have our models of friction. Remember that static friction is the force that opposes an applied force, and it is as big as it needs to be to keep the object from moving. So when it comes to static friction, S means static, it can be less than or equal to some maximum value, which according to the model, coefficient of static friction times the normal force between the object and whatever surface it's touching. And it could be as small as 0. So it takes on some range of possible values with a maximum. The kinetic friction, according to the model, is simply proportional to the normal force, and the proportionality constant is the coefficient of kinetic friction. So those are the relevant equations that we might need. In the first part of this problem, in order to figure out what the static coefficient of friction is, we're going to focus on the first piece of information we're given, which is that you have to pull with 230 newtons of horizontal force to start the microwave moving. In other words, that amount of force is the minimum required to get the object to move. That minimum amount must be the biggest possible, or just slightly more than the biggest possible frictional force there is. So in the first part of this problem, which I'll just call this part A, this statement about needing 430 newtons of force, what that tells us is that, 230 newtons of force, that is equal to the maximum amount of friction possible, mu s times the normal force. Now, since we need to know what the normal force is, we are probably going to need to use our free body diagram in some way. Let's rearrange this so that we are prepared to solve for the coefficient of static friction once we have figured out what the normal force is. In a problem like this, we are lucky that it's moving purely horizontally, which tells us something about what the forces are doing in the y direction. Clearly, this is the y direction, this is the x direction. And so let's just make sure that our assumptions are correct. The net force in the y direction is equal to the normal force, which is pointing up. And then because gravity points down, I'm going to insert a minus sign there to account for its direction. mg, that's all equal to the mass of the object times the acceleration in the y direction. We know that this object is not going to move at all vertically. Therefore, its acceleration in the y direction is 0. So this is all 0. That's how you can confirm that the normal force is simply equal in magnitude to the gravitational force, because there is no acceleration vertically. Now that we know this, we can come back and solve for the coefficient of static friction. Apparently, the coefficient of static friction is equal to 230 newtons divided by the normal force, which is mass times g. Mass times g, that is the weight of the microwave. That is this 500 newtons. That is equal to mg. So this is 230 newtons divided by 500 newtons, which gives me 0.46. The newtons cancel, as it should, because the coefficient of static or kinetic friction has no units whatsoever. So there you go. To do the second part, which we could call part B, in this case, now that the object is moving, we are going to be using kinetic friction. It's sliding. The microwave is sliding on the floor. So kinetic friction. Importantly, in this second situation, this statement about constant velocity is very important because constant velocity means 0 acceleration. So the acceleration is 0. That's useful when we go to apply Newton's second law, which seems to be the next logical step. We can apply it in the y direction, but we've already done that. We're going to learn the same facts, that normal force is equal to gravitational force. So let's go ahead and try to apply Newton's second law in the x direction. F net x. How do I figure this out? I look at my diagram. I've got an applied force pointing to the right, F applied. I've got a frictional force pointing to the left. I'll account for that with a minus sign. It's the frictional force. And I happen to know now that it's got to be kinetic friction or sliding friction. That's equal to the mass times the acceleration in the x direction. But we just got done saying that there is no acceleration because velocity is constant. So that whole right-hand side is 0. And so we're about ready to solve. This means that the frictional force is equal to the applied force. The frictional force obeys this model here. Mu k times the normal force is equal to the applied force. And we are nearly done. Mu k is apparently equal to the applied force of 200 newtons divided by the normal force, which we learned was 500 newtons, and therefore our coefficient of kinetic friction must be 0.4.